Okay. Hi, everyone. My name is Emmanuel Bimpon Manfo, and I'm one of the organizing committee members for this EVN seminar series. I am from Jodrell Bank Centre for Astrophysics and the Jodrell Bank Observatory at the University of Manchester. And on behalf of the organizing committee, I would like to welcome everyone to this series of online seminars sponsored by the European VLBI network, which focuses on high-resolution radio astronomy. Just before we make a start, I want to mention a few logistics of the webinar so that everyone can be aware of them. First, you all be muted throughout the presentation, but you are invited to type in your questions that you have for our speaker through the Q&A facility. And you can send in your questions during the talk or after the presentation. But please, we will only answer your questions after the speaker finishes their presentation. Please try to write your questions clearly and keep them simple and short. We will aim to get to as many of your questions as we can, but please, we apologize in advance if for time and different reasons we are not able to get to all your questions. Now, I will invite a member of the organizing committee, Kazi Rydell from INAF, to introduce our speaker for today.
Hello, thank you so much, Emmanuel. So Marica did her PhD at the University of Bologna and at INAF's Institute for Radio Astronomy, where I'm sitting right now. After a number of postdocs at the Urbino University and Caltech, she moved to the Gran Sasso Science Institute, where she is now a full professor. Marica is also associated to the Italian Institute for Nuclear Physics, INFN, to the Italian Institute for Astrophysics, INAF, and to the Italian Space Agency, ACME. So Marica started her career working at galaxy clusters in the radio and in the X-rays. However, early on, she already got interested in other carriers than photonic messengers, let's say. And she started to widen her research to include cosmic rays and in particular gravitational waves. She became part of the Virgo project, which is a Michelson interferometer to detect gravitational waves, and it's located nearby Macerata in Italy. As such, Marica was part of the first gravitational wave detection from a binary black hole merger, GW 150914, which is indeed a very iconic event. I even remember where I was and what I was doing when the news came out in February 2016. Marica is also part of the Einstein telescope, the next ground-based gravitational wave detector, for which at the moment 3 sites in Europe are in competition, and one of these sites is in Sardinia, Italy. Finally, Marica is part of the Horizons project, Astrophysics Centre for Multi-Messenger Studies in Europe, in which she is the leader of the working package for transnational and virtual access. So today, Marica will talk about exploring multi-messenger astronomy by current observatories and future frontiers. Please, the floor is all yours.
So first of all, thank you very much for inviting me. Now I'll share my slide. I hope that you can see them. Are okay? Yes.
Yes.
Okay, so today I want to make an overview of multi-messenger astronomy by current observatory, but also what are the future frontiers. So starting with the multi-messenger observation, I think that we need to come back to the first multi-messenger events, that is the core collapse supernovae that exploded in the Large Magellanic Cloud, for which we detected both the optical emission and the neutrinos. This event enabled us to probe the engine of core collapse supernovae, to set upper bounds on the neutrino mass, charge, and number of flavor, and also to perform a test of gravity. Then, after 30 years, we still observe this event, and in particular, there are ALMA observations, because one of the mystery was what is the remnant of this core collapse, a neutron star or a black hole. And more recent, there are James Webb Telescope observation that are showing with the HALMA observation some evidence that their remnant was a neutron star. Then there was the fantastic GB 17017, and I will talk a lot about this event. And we start to have also evidence on the sources of high energy neutrinos. So for example, there was this association with a flaring blazar, and there are more and more evidence that high energy neutrinos can form in tidal disruption events. But these events, why are so important? They are rare so far, so we don't detect many of them, but they really show us the potential of the multi-messenger astronomy that are able really to provide the physics of these extreme events, supernovae, gamma ray burst, AGN, tidal disruption event. But now I go on the clue of this talk, that is gravitational waves. So this is a more recent messenger that enable us to see things that before were not visible. So the observatory that make possible gravitational wave astronomy are in this slide. So we have 2 LIGO antenna in United States, Virgo in Italy, and also Kagra in Japan. These observatories are observing as a network. A network is very, very important because it enables us to analyze data all together in real time. To really increase the sensitivity of our search and also to localize events. So far we completed 3 runs of observation, and there is an ongoing run of 4 that will be completed on October. In this moment, our detectors are offline because there are some technological adjustment, and they will start soon to take data again. And as I said, in October, the 4 run will finish. So I go back on the first event that was incredible, was in 2015, and was a high signal to noise ratio signal. The signal was already evident in the raw data and extremely similar to the expectation. Why was so important? So first of all, because it was coming from it was a binary black hole merger, and was very important because told us really that the binary black hole exists in the universe, that they merge in the Hubble time, and also was a surprise the mass of this system. And the observation of this event and all the following one on the binary black hole merger were really very important on understanding the depth of a very massive star. So what happened is that we have run, and we typically stop the run, increase the sensitivity. So we make a technological upgrade, we increase the sensitivity, and each increase in the sensitivity is a larger volume in which we can detect sources. And this is clear in this plot. So our detection from a few in the first run became a lot now. So now we are around 300 detection. And the large majority of these detections are binary black hole merger. And what happened is that from the first event, now we have a lot of these system, binary black hole events. This is a 1, 2, and 3. And we can start really to make population studies. So we can start to have information on the distribution of mass of this system, on the spin-off of this black hole, and also on the rate. So for binary black hole, we have constraint on the local rate, but we start also to have constraint on the evolution of the rate with redshift. And now I go to the fantastic multi-messenger events in 2017. So we detected the gravitational waves, and 1.7 seconds later, we had this signal in the gamma ray from Fermi and integral. So these events, we put together the gravitational wave and all the electromagnetic signatures of these events, so all the band. It was crucial because combining the information, we now know much better the jet in gamma ray bursts. So it was important for relativistic astrophysics, for nucleosynthesis in the universe, And we started to put constraint on the equation of state of neutron star. From the gravitational wave signal, we can measure the distance. So if we have the distance from gravitational wave, and if we have the redshift of the host galaxy through the electromagnetic counterpart, we can have estimate of the Hubble constant. So this is a new way to make cosmology. Now we have very big error, so compared to supernovae and CMB, but the future machine, like Einstein telescope, will really will make it possible to have constraint not only in the Hubble constant, but also on the other cosmological parameters. And then with this combination of signal, we can also make fundamental physics. For example, the time delay between the gravitational waves and the prompt emission, so the gamma ray emission, enable us to measure the speed of gravitational waves, ruled out many modified gravity models. So how was this possible? So first of all, as I told you, we have real-time data analysis. So we can send alert very fast to the astronomical community. Now we are able to send alerts within minutes. Then an important parameter for the electromagnetic observation is the sky localization. Having a network of detectors is very important because the sky localization is done using the time delay in the detector. And these events were seen by LIGO and Virgo and was really well localized with respect to all the radars. So the localization was around 30 square degrees. Then what was extremely important was the multi-wavelength coverage. So all the resources in all the band were observing our binary neutron star merger. And what was clear is that is necessary to cover in all the band and also using different time scale. And the observation of these events were months, but also years later. So now I go in the details of this detection. First of all, this detection was the smoking gun evidence that at least a part of short GRB are produced by binary neutron star mergers. From the gravitational wave signal, in fact, what we extract is something that is difficult to extract from the electromagnetic emission, that is masses. The masses of this system was consistent with the new neutron star in our galaxy. Another parameter that is extremely important that we can extract from the gravitational wave signal is the tidal deformability. The tidal deformability is important because it's directly connected to the equation of state of neutron star, but also to the amount of mass that is destroyed during the merger, that is the mass that then gives rise to the electromagnetic emission. In this plot, you can see the tidal deformability for the two components, for the two neutron stars, and the blue region is the region more probable, and the lines correspond to different equation of state. So from the gravitational waves point of view, we were able to exclude the less compact neutron star, the harder neutron star. Vice versa, if we take the electromagnetic emission, this event was extremely bright, so a lot of ejecta, and so we ruled out the soft equation of state. So we have constraint in opposite direction. And this is extremely important because this event can really constrain the equation of state of neutron star. Then looking at the gamma ray emission, this emission is what we typically classify as a short gamma ray burst. But then knowing the distance and comparing our object with all the GRB detected so far, this event is fainter. And so the first question was, this is something intrinsically fainter or this is a short GRB observed off axis? So the gamma ray emission is a beamed emission. When the jet, the relativistic jet, interact with the interstellar medium, decelerate, and what happens is that the emitting surface increases. So an observer that at the beginning is not able to observe the emission, start to observe the emission, and so the emission is observed later and fainter. So these are the first detection that we had in X-ray and radio. So for many days, there were search for X-ray and radio emission, but we didn't have any detection. And then we have a detection in the X-ray and detection in the radio. So in this plot, that is a plot of one of the papers that came out with the press release. What you see here is in light gray, the emission expected in X-ray for an on-axis emission. And then you can see the detection here and no detection before 9 days. So what you see here is that these points are consistent with the line that corresponding to off-axis GRB. So what the first papers were talking about an off-axis GRB emission. In reality, considering a top hat jet, so a jet without an angular distribution of the velocity, what we expected was a decline of the flux. Then, for many, many months, what we observed was an increase of the flux. So this increase of the flux is consistent with two scenarios. One in which we have a structured jet, in which we have a faster component of this jet at the center, and then a angular distribution of the velocity, a slower jet at the border. Then we have another scenario that can explain the same increase, that is an isotropic outflow that can happen, for example, in the case of a choked jet, a jet that is not able to escape from the ejecta. In this case, we have a faster component outside and a slower component inside. And again, what we expect is the same. So if we look to the light curves in all the bands, so X-ray, optical, and radio, the increase and the light curves were completely consistent with both scenarios. And here, what was critical was radio observation, the resolution of radio observation, because the expectations are different on the source if you consider a successful jet or a choked jet, so this isotropic outflow. In the case of a successful jet, we expect a larger displacement of the source with respect to the merger place, and what we expect is a smaller size of the emitting region. And so what we did was 200 days later to take observation through VLBI, in particular 32 radio telescope. And this was really critical because it was the observation that told us the source size and told us that the source size was smaller than 2 milliards-seconds. And this ruled out the isotropic outflow. So thanks to the radio observation, we are able to say that there was a relativistic jet, like in short, a typical short gamma ray burst, a structured jet that was observed off-axis. Another way to discriminate between these two scenarios is also through the polarization, because a successful jet is expected to produce a larger polarization. There were VLA observations to measure the polarization. They were not able to constrain the scenario, but within the structured jet, they show that these type of observation are important to put constraint on the magnetic field configuration in the shocked jet. Then I go to the thermal emission, and in particular the Kilonova emission. So when we have and what these emissions say to us, that binary neutron star merger are one of the major channels of formation of heavy elements. And we can say this on the basis of the binary neutron star merger rate that, so now with gravitational wave we started to measure. and also on the basis of the ejecta, so the brightness and the evolution of the ejecta. So when we have a binary neutron star merger, what happens is that when the two neutron stars are closed, they start to be destroyed, and so we have a material that is really very dense of neutron and with high temperature. And this is a perfect site for nucleosynthesis of heavy elements. So we produce air process nucleosynthesis. We have these elements that then radioactively decay when the ejecta is enough expanded. We have the electromagnetic emission. We start to observe electromagnetic emission. And this emission is expected in the red infrared band, and typically is expected to last days, week. But then we have other component of the ejecta, for example, the shock-heated ejecta, the accretion disk wind outflow, the secular ejecta. Here, the temperature that we expect is higher. We have a weak interaction. We have a lower fraction of neutron, and we are not able to form the very heavy elements. So we form elements more close to iron. The opacity is lower, and we expect an optical, a blue optical transient in the first days after the merger. And this was exactly what we observed. We observed a blue component at the beginning and then a red component. We took fantastic spectra with the VLTX shooter. And so what we observed was the absorption feature typical of air process nucleosynthesis. So it's not like in a supernova in which we have line and we can identify the single elements. Here we have a forest of line because we have a very high atomic level, a lot of atomic levels, and the ejecta is very fast. So we have a lot of this mix of lines and so with different velocities. So we expect absorption feature. And let's say that I think that one solid evidence of one element is in this plot, in which we can say that this absorption feature can be connected or are connected with strontium. So what happened after GV17017? We had another binary neutron star merger in O3. And this event had a very large scale localization, so no electromagnetic counterpart. But this event is very important because it shows us that so the binary neutron star can have large masses, larger than what we observe in our galaxy. This system have a total mass that is larger than all the systems that we know in our galaxy. And this is important because when we make simulation with this type of events, for example, for the Kilonova emission, the emission is much fainter with respect to GV17017. So we had also neutron star black hole. Also this one can have an electromagnetic emission. There are a lot of models. We detected two, for sure, there is a candidate. We had other candidates in O4 that needs to be confirmed. But at least for these three, there was no electromagnetic emission. But it is also expected for the type of system because what we detected was neutron star black hole in which the mass ratio is high. So the black hole is pretty high, is a pretty high mass with respect to the neutron star. What happens when we have this system? That when the black hole have a high mass, the neutron star fall down in the black hole before being disrupted. So we don't have material around to give rise to the electromagnetic emission. We expect electromagnetic emission when the difference between the mass of the black hole and the neutron star is smaller. So what typically do in gravitational waves is to search in real time and send alerts, but we do also another type of multi-messenger search. So what we do is that when we have a gamma ray burst, a fast radio burst, a flaring magnetars, a supernovae, or a neutrino events, what we do is to use the information of these candidate multi-messenger sources. And we use, for example, for gamma ray burst, we use the distance of the gamma ray burst, the position of the gamma ray burst in our search for gravitational waves. This is extremely useful because it increases the sensitivity of the gravitational wave search. But what I can say is that after GV170817, we didn't have any other multi-messenger events. But no panic, because binary neutron stars are there, and I think that the future is very bright. And I want to say you two very interesting events that were detected when the LIGO and Virgo were not observing. So we detected two long gamma ray bursts with kilonova emission. So this means that a fraction of long gamma ray burst comes from binary neutron star or neutron star black hole merger. And what was interesting was that these two events are really at a distance that is reachable by LIGO. And so they were in a moment in which there were no observation, but this means that so they are there. And so we wait for another GV170817 event. I want to tell you what will happen in the next years. So what will happen is that our detector, LIGO and Virgo, will increase the sensitivity. So we have a plan of increasing of the sensitivity. We have already some project also to bridge this detector to the future one. In particular, in Virgo, there is the Virgo Next, that is a project of large upgrade of the current detector. And for LIGO, there is LIGO Sharp. Then there is also LIGO India that will join the network. It is expecting in between 2030 to 2035. So we will have a network of detectors with increased sensitivity, so a larger volume of universe that they will detect, they will observe, and also the network that is very, very important for the sky localization. Then we have a lot of new instruments that will come online, the very Rubin Observatory that is extremely important for transient, instruments like SOX that are used for spectroscopy of transient, ELT that enable the detection and the spectra that we have for GV170817 for more distant objects, SKA for the radio. Then we have instruments like wide field in the UV that are very important, for example, for the first component of the Kilonova, and also new instruments in the gamma, very high energy. So some of them already started observation. There are others that are expected next year. This is not a complete scenario, so there are many, many others, but give you a sense of what will happen to the transient astronomy and multi-messenger astronomy. But now I want to go to the next generation, because also there we have really fantastic simulation that show us what will be the future. So in Europe, we have a project that is called Einstein Telescope. This is the European Next Generation Gravitational Wave Observatory. A few years ago, already passed the S3 roadmap, so is in the S3 roadmap. So this is a priority for Europe, a priority infrastructure for Europe. The collaboration, the Einstein Telescope collaboration is now of more than 1,700 people, so much, much larger than the gravitational wave community, because there are cosmologists, nuclear physicists, astrophysicists, so it's really a huge community. So we are studying two design that is a triangular shape or 2L located in Europe. This is an underground facility because we want to reach lower frequency with respect to coordinate detector, cryogenic, and xylophone. Xylophone means that to increase the sensitivity both at high frequency and low frequency, the high and low frequency detector will be separated. So in the plot are the red and the blue one. So there are 3 site candidates to host the Einstein telescope, and in particular, there are Sardinia, one in Netherlands, and one in Germany. The geometry and site selection is expected by the end of 2026, and the operation are now expected around 2035-2040. So ET, with respect to the current detector, we will have an increase of the sensitivity of at least a factor 10 at all frequency. But what is really very important is the access to the lower frequency. And all these, what we'll do. So the low frequency is extremely important because we want to reach the early universe. So since the masks that we observe in our instrument are redshifted, what happens is that if you want to observe the binary black hole that we observe today in the early universe, we need to go to lower frequency. And there are also the binary black hole coming from the first star, so POP3 star, and we aim to detect also primordial black hole. So we will observe gravitational waves from all the universe, the observable universe, and really we can start to talk about population study across the cosmic history of the universe. And for the closer events, we will have a signal to noise ratio extremely high. So we will have routinely events with signal to noise ratio higher than 100, and some of them also higher than 1000. So this means that we can start to talk about precise gravitational wave astronomy, because today we don't have precise gravitational waves astronomy, because when we estimate the parameter, we have really big error. And so precise gravitational wave astronomy will be possible with the Einstein telescope. So the science that the Einstein telescope can do is extremely broad. Here there is a summary. I don't talk about this because it will take 1 hour, more than 1 hour. And the only things that I want to say is that recently we published as observational science, as collaboration, ET collaboration, we published the ET science book that show all the science that ET will do. But I want to go more on the multi-messenger side, and what I want to show you a few numbers. So these are the expectation for ET. In blue in this plot, you can see population of binary neutron star and binary black hole that we produce with population synthesis code that are able to reproduce what we know today about binary neutron star merger and binary black hole mergers. And what we can say is that ET will be able to detect 10 to the 5 binary neutron star per year and 10 to the 5 binary black hole per year. So the number of detection expected by ET is really large. One of the key parameters is sky localization. So ET is able to localize alone long signal like the one of binary neutron star. Because what happens is that we can detect this signal at low frequency so the signal is in the band thanks to the low frequency also for hours. And so what happens is that we can use the imprint of the Earth rotation in the signal to localize the event. And these events are also the one for which we can send early warning alerts. So send alert to the astronomical community before the merger. In United States, there are a different concept for next generation. It's Cosmic Explorer. It's a surface detector, 40-kilometer detector. Likely there will be also a second one of 20 kilometers. They want to improve mainly the high frequency. And if ET will observe with Cosmic Explorer, we will have thousands of detection per year with sky localization less than 10 square degrees. So again, the network is very important. In my slide, time to time, you will see this fish. This is a code that we use to make parameter estimation for this big population of binary pulsar binary black hole. Is called GW fish. Is a Fisher matrix code, totally open. And what I want to say is that the majority of the things that I will show you today, there are catalogs of the things of the parameter estimation that we did with this code that are totally public and can be used for all the study that you would like to do. So one of the things is pre-merger detection. This is very important because we can detect pre-merger, but the important thing is not only that we can detect pre-merger, but we can localize pre-merger. And for example, ET can localize tens of events with sky localization less than 30 square degree minutes, 5 minutes before the merger. And we start to do also study, for example, to use these pre-merger alerts, for example, to detect the very high energy with also CTA. One of the big problems will be that there will be too many alerts. And it's not like today that when there is a gravitational wave signal coming from a binary neutron star, all the resources, observational resources, are pointing in the sky of the binary neutron star merger. So we will have so many events that will be extremely important to select. And more than now, it will be necessary that the selection is based on science project. And another thing very important is that internally in Einstein telescope, we will not be able to make the refined parameter estimation for all the events. And so we will be also listening when there will be a Gerbein coincidence with a gravitational wave. These events will be the one that will be selected for first to make the parameter estimation better. So there will be a change of paradigm in multi-messenger astronomy. And what will happen is that in the closer universe, where we have also precise parameter estimation, we can detect, for example, kilonova emission that is intrinsically fainter. And we can arrive up to 0.3, 0.4 with instruments like the Vera Rubin Observatory. But then when we want to detect counterpart at higher redshift, we need high energy satellite. We need to detect the prompt emission. And so we will have a lot of gamma ray burst. So I give you a few numbers. These are all plots come from the ET Science book. And here you can see the detection rate as a function of detection limit. In this plot, there are no instruments involved. There are no, so it's not, the number are really optimal number because there is no duty cycle, no sky coverage. But from this work, when then we look also to the to specific instrument, what we can say that all detected short GRB will have a gravitational wave signal. So each short gamma ray burst will be a multi-messenger source in the future. Now, as I told you, making study more refined and looking at specific instrument, what we can say that instrument like Theseus, that is one of the candidates for the ESA launch mission in the 40, Theseus will be able to detect tens of events in which we will have also the gravitational wave signal. Instrument like CubeSat, a constellation of cube satellite like Hermes can detect hundreds of them. The difference is that Theseus is also able to localize. So we need also instrument able to localize, then to drive the follow-up by ground. Then also X-ray telescope will be extremely important. This will enable us to detect the afterglow emission and are important because they will enable us to detect also off-axis GRB. And in particular, so these are important because they increase the number of detection and are extremely useful to understand the structure of the jet. And then also instruments like Athena and Axis to characterize really the afterglow emission. Now I go to the afterglow emission of the band. So in this plot, you can see the afterglow expectation in X-ray, optical, and radio. So the first two plot, the first two rows correspond to binary neutron star. And here are two models of Schrödinger B. And in particular, these two models are both able to reproduce the observation of all Schrödinger B. And we want to give it also different model to show the difference also in the rate. And here you can see the expectation in radio, optical, X-ray. The solid line corresponds to all the events, and the dashed and point line corresponded to following only events with a sky localization less than 100 square degree or 10 square degree. And here I also put the what you expect, for example, for SKA in 1 hour of observation, and the number of possible detection is really significant. Then for thermal emission in Kilonova, this is the plot in which we have again detection rate as a function of detection limit. Again, also in this case, we did also more realistic observation. So what we explored was the Einstein telescope with the Vera Rubin Observatory. And here we did a lot of simulation, taking into account different BNS merger population, 10 years of merger. And then what we did was also exploring different neutron star mass distribution. We don't know so far the mass distribution of neutron star. Different equation of state, several network. Then we make a population of likers taking into account GV 17017, but also GV 190425. Then we use realistic observation with the Vera Rubin, in which we consider target of opportunity, and we consider multi-filter that is necessary because we have a lot of contaminants, so it's also difficult to find the counterpart. And the work told us that with Rubin, we will have 10, 100 kilonova detection per year. And if Einstein telescope will observe with the current facilities plus LIGO India, we can increase by an order of magnitude the detection of ET. And ET plus Cosmic Explorer, we can increase further, but not so much, because we are limited by the limiting magnitude of the Vera Rubin. In this case, we consider an exposure of the Vera Rubin of 600 seconds. And so this is what will happen to multi-messenger astronomy. So I show you that all the Schrödinger B will have a gravitational waves. The afterglow emission in all the band is very promising, and also in the optical band. So so multi-messenger astronomy will become really a routine. Now we have rare event will become a routine. And in all these fantastic scenario and perspectives, I think of multi-messenger astronomy in this emerging field that is extremely important to understand the physics of this extreme universe. We have an opportunity for Europe. Is a European project, ACME, and ACME has the main objective to access the best research infrastructure in astronomy and astroparticles, so connecting astronomy and astroparticle, and want to offer access to state-of-art instrument and also virtual center of expertise focused on multi-messenger astrophysics. So this project is coordinated by Antoine Kochner. The deputy PI is Paolo D'Avanzo, and is structured in 7 working packages. And in particular, I will focus on 2 working packages. First of all, the consortium, let me say, is with 40 partners, nodes of multi-messenger nodes distributed in Europe, 15 countries, 30 research infrastructure. We will cover radio, optical, near-infrared, X-ray, gamma rays, gravitational waves, neutrinos, and cosmic rays. And so two working packages that I think are very interesting, with a lot of call for interest, so call that gives opportunity to young research and also older one. So working package 2 is devoted to transnational access, so give observational time in the instruments that you see in the plot is extremely important, and wants also to facilitate innovative science like it is multi-messenger astronomy. And you can see here that instruments like kilometry net, Pieroget, CTAO will give access to their observation. And then the other one is working package 3. Here I work with Zsolt Paragi, and here what we want to give is provide scientific expertise. So everything is done through 6 centers of expertise. Each center of expertise have distributed nodes. In the plot, you can see also all the instruments that are involved, and we want to give direct training and expert guidance in multi-messenger astronomy, and in particular expertise on the observatories, on the observations, on the advanced data analysis and theoretical tools. And all these to analyze and to interpret multi-messenger observation. And I go to my last slide. I hope that I didn't take too much time. So I think that multi-messenger astronomy has really a bright future, that ACME is a European opportunity to build a multi-messenger community in Europe to train young people that will drive also the future detector. And the next generation detector will really make multi-messenger astronomy a routine, and will enable us to understand the extreme events in the universe. And this is my last slide.
All right. Yeah. All right. Thank you very much, Marica, for such a wonderful presentation. I'm sure our audience have learned a lot, and I've also learned a lot. Thank you very much. So we have just about probably 10 minutes or so for questions. So if there is any question from any of our audience, please feel free to type it in the chat, or you can raise your hand and I will call you to quickly ask your question. Okay, whilst we wait for questions from the audience. So Marica, just a quick one from me. Oh, okay. I will not abuse my powers or privileges, so I'll ask Zsolt to ask the question.
Sorry, I didn't mean to silence you. I was just anyway. I was just wondering about this ET telescope. It will be a fantastic instrument when it's built. And you mentioned already what are the other messengers, or what other observatories how can contribute to this. But so I understand that primarily it will be the lower redshift universe where we have a chance to detect in many other bands, right? And then you said that at the highest redshift it's probably just the gamma rays. So how critical is for the ET to deliver the science these other bands, or what do you see the opportunities are for us here?
No, here I think you have a lot of opportunity, because if you think that in the radio, in some sense, you are detecting the more closer universe with respect to the distant one, there is also where we have precise gravitational wave parameters. And so it's really where we can constrain the physics of single events. And so I think that there it's extremely important, because we really can impact the physics of single events. When we think about a larger volume, there we can increase population studies, and also there we can have a lot of information. But I think in the closer universe, we can really benefit from this parameter estimation of the progenitors of our source that are really very important to understand the engine, to understand the ejecta, to understand also the jet. So I think that this is the part in which really radio will be crucial, and also VLBI we saw in GV17017 the importance.
Yeah, thank you very much. Just thinking a bit more broadly than the radio. So thinking about these standard candles in particular. So if we want to use them for cosmology, we need to know the redshift,
Yes.
right? So then, sorry, I should have looked in the ET book. I will download it. But so was there a study done how far away this could be useful because you need the optical detections?
Yes, so you are totally right. So the thing is that we can make a reality cosmology in different ways. So one of these ways is using bright sirens. So the one in which we have also the galaxy and we have the redshift. So there is very important to look at the sky localization. So try to see up to where we are able to have good sky localization to limit the possibility of the host galaxy and then the electromagnetic counterpart. It's clear that if we want to go more distant there, it's very important to have, for example, the short gamma ray. The short gamma ray burst that is detecting in the gamma ray, but there are also some projects that are trying to detect the prompt optical emission. So it's not only really the gamma ray, but detecting the prompt emission of gamma ray burst. And there, at that point, if we have a very good sky localization, we can identify the galaxy and make the cosmology. The other way is using binary black hole for cosmology, and there we use statistical approach in which we use the galaxy catalog, and the Euclid will be extremely important because we will have the distribution of the mass of the galaxy. And so this part will be important. Another way is also don't using the electromagnetic counterpart, but if we are able to constrain, for example, the mass distribution of neutron star, this can be used, so we can use only the gravitational wave signal to make cosmology. But the way in which we have smaller error is with the bright sirens, also with the electromagnetic counterpart.
Thank you very much.
All right, thank you very much. Ionis, you've got your hand up. Yeah, please go ahead.
Yes, thank you very much for this very nice talk, and please ignore my ignorance if this question is too naive. But you mentioned the very nice prospect of low frequency gravitational wave detection with ET. I want to ask, does this mean, does this open the detection to supermassive black holes or intermediate mass black holes? Is still too small for something like this?
No.
Maybe?
So yeah, so we will arrive, lower frequency for us means frequency lower than 15 Hertz, let's say. So we will arrive we hope to arrive to 3 Hertz, but
Okay.
then we cannot go to lower frequency. So if we want to go to lower frequency, there is LISA. And now, so there are new projects also for the Hertz band. And for example, there is the possibility to use the moon. And there are, one of these projects is, for example, the lunar gravitational wave antenna that we use the vibration of the moon when a gravitational wave passes. And there you can detect it, for example, events that can be connected for tidal disruption events, like so intermediate massive black hole with a star around.
Okay. Okay.
All
Thank
right.
you.
Yeah. Thank you very much. We've got some questions from YouTube. So George is asking for neutron star measure detection predictions by LIGO Virgo was about 0.4 to 400 per year, which were far too optimistic. So George's question is, what went wrong with predictions, and have these issues been corrected for ET expectations?
No, okay. So in reality, we had big uncertainty in the BNS rate. So still the fact that we are not observing is still inside what were the prediction. We didn't have observation, so it's clear that when you don't have observation, the prediction are not constrained. So the range of rate was pretty large. We are still inside. It's correct that we are moving to the lower rate because we don't have detection of neutron-star merger. All what I show you today is consistent for ET, is consistent with the binary neutron-star merger that we had so far. So it's also considering the fact that we don't have detection now. So all that I show you is consistent with this. It's clear we have big error in this number. So when I show you the number of kilonova, this number can be a factor of 5, 6 lower, or also a bit higher, but not so much. On the GRB side, what I told you today are not depending on the BNS rate because everything was calibrated on 40 years of observation of gamma ray burst. So it's true that we are going to the lower range of binary neutron star, but the prediction that we did, that I show you today, are consistent with the current observations.
Well, can I intervene a moment? Marica, is Remo calling? Can you hear me?
Yes, we can hear you. Please go ahead.
I think we are all in a very exciting time because we are understanding in GRB many details, new, in particular around the prompt. And one great news is that in some of the more energetic GRB, we see the possibility to have a very fast spinning millisecond pulsar, which goes from Maclaurin to from a Jacobi to a Maclaurin, and possibly emitting gravitational waves. I would like to urge the people I'm contact already the people in Rome to see if we can correlate the observation of this GRB with the gravitational wave detector. The other very important result is for the first time we are able to measure the mass of the black hole in GRB, in long GRB, and it is very exciting because it's around 2.3 solar masses, and we have 3 examples in which we can give all the details and the time of appearance of the time and the energy of the emission of the black hole of 3.4 solar masses. This is extremely exciting, and we would like to discuss with you also on implication for 170817, but especially the novelty are the data of Cygnus X1, which I go to present at the Italian Physical Society, that the new mass determination of Cygnus X1 points to the possibility of having 20 solar mass binary, each component binary neutron star. And that should be of interest to you. We have data on this system, and it's very exciting.
All right. Thank you very much.
If I can add something about this, I didn't touch one of the promising things, that is detecting the emission from the remnant, the gravitational wave emission from the remnant. That is extremely important because it's connected then also to the electromagnetic emission, as Remo said. And this is another field in which we are with the current detector also trying to detect the post-merger signal. It's very hard with current detector. With ET is very promising. So there we have the sensitivity that is at high frequency to detect the post-merger. And this is really very important to understand the engine of the GRB, absolutely.
All right, Yeah, thank you very much. So it's time actually, but there was one last question from YouTube that I wanted you, if you have time, Marica, to respond. Yeah, so this is from Tonino. Tonino is asking, from a scientific point of view, is it better to build ET in a triangle or with an L-shaped configuration?
So triangle to L, the question is.
Yes.
No. Yeah. Okay. There is a work that we did inside the Observational Science Board. I didn't talk about this, but we explored the science, the impact on science using triangle and 2L. Let's say that we compared a triangle of 10 kilometers with the 2L of 15 kilometers, located one in Netherlands and one in Sardinia. So what we found is that for all the parameter estimation, almost all the parameter estimation, we have an improvement of a factor 2, and also in the number of detection of at least a factor 2. So this is clearly something that is important, a factor 2. Someone can say, okay, in a population of 10 to the 5, a factor 2 is nothing, but it is also an explorative instrument. So we want to arrive to the early universe. We want to detect POP3 binary black hole mergers. We want to detect, so this factor 2 for this explorative part is critical. So ET triangle is fantastic. 2L can do better.
All right. Thank you very much. I think we are just 3 minutes past time, so we will end the Q&A session here. And we thank you, Marica, once again for such a wonderful presentation. Now I'll hand over to Benito to give us just some quick announcement for our next seminar.
Yeah, thank you. And great seminar, Marica. Just a very quick announcement. So we will continue the EVN seminars in October. Miguel Perez Torres will be our next speaker. We will see the abstract and the final date soon. And then after that, at the end of the year, we will continue in November, December by Sandor Frey. And the last one is like the registration is still open. Like we are organizing the GI BLBA school to learn how to analyze EVN data so it can help on all the science that Marica has been talking about. And then the school will be in a hybrid mode from 15th to 19th of September with 2 venues. The main one at JIVE in the Netherlands and the second one synchronized and in streaming in the University of Pretoria in South Africa. And then we will also accept online participants only. So if you're interested, please register there. And with that, I think we can conclude the seminar. Thank you, everyone, for joining us.
Well, we have hello. We have a meeting on the 4th of June in Tartu, and everybody is interested in participating, and we will present there many topics, including the large-scale structure of the universe with Einasto, but especially the red dots with Professor Louis Ho and many of the people of ICRANET. You are all invited.
Thank you very much for the contribution.